Okay, so in this video, we're going to cover section 2.2, and that's on graphs of functions. Let me share my screen. Okay. Okay, so this, as I said, is section 2.2. This is on graphs. Functions. So in the last video, I introduced the idea of a function. And a function is a rule of associating an element in one set, the domain, to an element in another set, the codomain. So a function sends elements in its domain to elements in its codomain. And it does so by some rule, some well-defined rule. So for example, you could have the function f be equal f of x equals x squared. And the rule is that it takes every number and squares it. So the domain on that, which if you recall, is the largest set of numbers for which the rule makes sense or is defined. So the domain of that function, x squared, is all of the real numbers. The codomain, again, is all real numbers. But the range, which is a specific set I introduced, is the set of all outputs, is the range of the function x squared is all the non-negative numbers. So, and this is an example where the range does not equal the entire codomain. So in this section 2.2, we're going to look at graphs of functions, and graphs and plots are sort of used interchangeably, but they don't mean the exact same thing. A graph of a function is actually a set. So again, this is the importance of sets, which is why that was the first thing we talked about. That was the first lecture, was just on set theory, or just like the fundamentals of set theory, because sets are very important in mathematics. So the graph of a function is a set. The plot of a function is this, like a pictorial representation of this set. So when you plug a function, so we represent functions in the plane. We can do this two-dimensionally. And so the input is your x coordinate, and then the output of the function would be with a y coordinate. So let me write down a definition, just summarizing all this. So this is definition. This is graph of a function. So if we have some function, say from A to B, where A and B are subsets of real numbers, then the graph of f is the following set. And so I'll just call it graph of f, and it's the set of all x comma f of x, where x is a number in the domain. So a and b, so if f is a function from a to b, takes elements in a and sends them to b, elements in b, by some rule. It's not specified what that rule is, but there is a rule associated to f. And a and b are subsets of the real line. And we define the graph of f as the set of all ordered pairs x comma f of x, where x comes from the set A. So this is obviously the x coordinate. And the f of x is going to be our y coordinate. So the x the f of x is basically going to give us the signed height. So maybe I'll put this in parentheses, the signed height of the graph or plot of the function f. So I'm using, I'm kind of abusing notation. I'm using, or terminology, I should say. I'm using these terms sort of interchangeably, but really graph refers to this abstract set, and then you can draw the graph. But the y coordinate is f of x, and this is assigned height because the graph could be above or below the x-axis. And I should actually say this is the signed height to the x-axis. Add that in. So the y coordinate is f of x, and it's the signed height of the graphs or plot of f to the x-axis. So let me just give you a little example. So we have, say we have something like this. So maybe our plot is like this, and maybe the set A goes from, I don't know, let's say 1, I don't know, let's just be more general, A to B. So the set, our set is this interval A to B, and then this is right here the range. So this would be f of A, f of B, and then this point right here is A, f of A, and this point right here is B, f of B. And then we can just take some arbitrary point in the set, say right here, this will be x, and this point right here will just be some point other than the endpoints, x, f of x. And so this right here, the y coordinate is the height of the graph at that point. So this height right here is f of x. Now, of course, the graph could be below the x-axis, and so that would mean your y-coordinate is some negative number. So f of x would be equal to some negative number. But it would be like a signed height. Or maybe more concisely, you could say the absolute value of f of x represents the distance or the height of your graph, the graph or the plot of the function. So this is just an example here. So this curvy line right here is a plot of the graph. So this is not the graph, strictly speaking, this curved line right here is not the graph itself, but it's a plot of it. And hopefully this will just illustrate exactly what this set is. So we can, some of these sets we can just plot, some of these functions we can get by plotting points. So let's look at just one example. This is a pretty simple example. We might have even done it before. So let's just look at the function f of x. So f goes from real numbers to the real numbers, and the rule is given by squaring. And so we want to plot the graph of f of x. And that will be all the x, or it will consist of ordered pairs, just going by definition. So the graph of f will consist of all the ordered pairs x comma f of x, where x is some real number, because that's our domain. This is the domain of the function. But we know what f of x is. It's just x squared. So the graph is the set of all pairs x comma x squared, where x is some real number. And we can describe some of the elements. So let's look at some of these elements. So this set will consist of some elements like 1, or let's actually, so it could consist of, say, -1, and if x is equal to -1, then the y coordinate will be this, and we can simplify this to get this. So this might be a point. This is an example of a point in the set. And then this would be another point in the set. And then we could have x is 2, and then this would be another point in the set. So -2, and then -2 squared would be 4. And then we have 2. And if x is 2, then that means f of x is 2 squared, which would be 2, 4. So this is just some points in the set. Of course, it consists of a lot more. It consists of an infinitude of points. But these are just some examples of points in the set, and we can use these to plot the function. So actually, I should include one other easy point you can calculate. So if x is 0, then f of x would be 0 squared, which is just 0, 0. So that's going to be a point on this, the plot of the set, of the graph, the set when we plot this. And then I have -1, -2, 1, 2. So when x is 1, f of x is 1. 3, 4. When x is 2, y is 4. Or when x is 2, f of x is 4. When x is -1, f of x is 1. And then when x is -2, f of x is 4. This is what we determined up here. So I'm just plotting these points. We got 1, 2, 3, 4, 5 points that I'm plotting. And this will just give a very, very rough picture of what this thing looks like. It's very rough, but it's supposed to be a parabola. So this is just a graph of the function, or it's a plot of the graph of the function. So that's all I want to say for that example. You can graph these using calculators, and the book gives you in some instructions on how to do that, but we don't really need graphs. So let's look at some piecewise functions. So I introduced, in the last section, I introduced a piecewise function, and a piecewise function is, again, a function, but it has its domain split up into parts, and on each part there's a different rule associated to the parts. You evaluate the function differently depending on what part of the domain you're looking at. So let's look at example 4. So we have this function. It goes from the real numbers to the real numbers. So the domain is the real numbers, the codomain is the real numbers. The range might be different than the codomain, because that can happen in general. And the rule or rules of the function are as follows, because this is a piecewise defined function. So it's f of x is equal to x squared if x is less than or equal to 1, and it's equal to 2x plus 1 if x is strictly greater than 1. And we can calculate some points. So if we can determine some points on the plot of this graph. So if f is, let's say, 0, or if x is 0, then 0 is less than 1. So that means we evaluate the function according to this first definition right here, x squared. So we get 0 squared, which is just 0. So that implies 0, 0 is a point on the plot, or it's a point in the graph. If x is 1, then again, because 1 is less than or equal to 1, we use the first part of the definition to graph this. So we get f of x is equal to 1 squared, which is just 1, and that implies that 1, 1 is a point on the graph. Now, when x is, say, 2, 2 is strictly bigger than 1, so we use the first part of the definition we use the second part of the definition to evaluate this. So we get 2 times 2 plus 1. This will be 4 plus 1 is 5. So that implies that 2, 5 is a point on the graph, and then maybe just one more point, and then that'll enable us to plot the graph. So when x is 2, when x is 3, 3 is strictly bigger than 1, so that means we use the second part of the definition of f to evaluate it to determine the output. So we'll have 2 times 3 plus 1. 2 times 3 is 6 plus 1 is 7. So that means that 3, 7 is a point on the graph. So all these, I'm going to use the set notation. These are points. This means in the set graph of f. So just some points, not all of them. And if you use these points, I'm not going to be precise. I'm just going to sketch the graph. You will get the graph of this will look something like the following. So we have this breakpoint at 1. So remember we have the domain is all of R, but there's a break at x is equal to 1. The domain sort of splits up here. So we have to be careful about graphing this function at 1. But if you are careful enough, you'll see that the plot looks something like this. We have a hole at here, and then we have a straight line, and then we have a solid circle, and then we have a parabola for the other part. So when you take x values less than 1, you evaluate the function as a parabola. So it makes sense that less than 1, the graph should look like a parabola. And the graph should look exactly like a parabola at x equals 1, because when x equals 1, you're still evaluating it according to x squared. So it's going to still look like a parabola at that point. That's why we have this solid circle right here. And then when x is strictly greater than 1, but very close to it, now it's going to start looking like a line, a straight line, because when x is greater than 1, you evaluate it as 2x plus 1, which is the graph of a line. So that's why we have a solid circle here, because it doesn't look like a line at x equals 1, but it looks like a line very close to it, and for all x values greater than 1. So this will be a rough graph of the function. So this is, right here we have f of x is equal to x squared when x is less than 1. And for this part right here, this other part of the graph, we have f of x looks like 2x plus 1 for x strictly greater than 1. So as I mentioned this once before in the video, one of the previous videos, that it's not always the case that a plot of something will have an algebraic expression associated to it, or a function in our case. So this next thing I want to discuss is the vertical line test. So this gives us a way of determining whether a given plot has a function associated to it. So the vertical line test allows us to answer the question, given a plot, is it the plot of some graph? So the vertical line test is as follows. It says a curve in the coordinate plane is the graph of some function if and only if, and this is important, if and only if, no vertical line passes through the curve more than once. So it can intersect the curve at most at one point, or maybe at no points at all. But if it intersects the curve at more than 2 points, it can't be a function, or it can't be the graph function. And why is that? Well, let's go back to our notes from 2.1 where we gave the definition of a function, and it'll be clear why that can't be the case. So a function f is a rule that assigns to each element x in a set A exactly one element in another set. I should put here another set B, and this output is called f of x. So the keywords here are exactly one, and that will tell us why this will actually prove why the vertical line test is valid. Let's see why. So suppose we have the following curve. So this is just going to be, it's going to represent an arbitrary curve in the plane, and say it looks something like this. Now, if we draw a line through here, a vertical line, it's going to cross through 2 points on the curve. Now, let's say, so it's going to cross at, say this is B, or no, this is, sorry. So it crosses over here. This is x equals A, and then this will be B, and this will be C. So this point right here is A, C, and this point right here is A, B. Now, let's just, I'm going to use a proof method. It's going to sound odd, but it's going to be proof by contradiction. And the idea behind a proof by contradiction is you have a claim that you want to prove. Now, any statement either is true or is not true. So this is the law of excluded middle in logic. If you take a course on logic, they'll introduce you this so-called law of excluded middle. And what that basically says is that for any proposition, a proposition is just either true or false. There's no middle option. There's no third option. A proposition is either true or false. And a proof by contradiction basically relies on this fact in the following way. It says, okay, well, suppose you have a statement or a proposition you want to prove. So if and suppose you know it's true, but you don't have a direct way of proving it's true. Well, you can prove it in the following way. Suppose it's false. Suppose the proposition is false. If you can then, from that assumption, from that hypothesis that the proposition is false, if you can derive a contradiction, then you will prove that your assumption was wrong, namely that the proposition is false, and therefore the proposition has to be true, because otherwise it will imply a contradiction. Like, for example, imagine you suppose some statement is false and it implies something weird like an integer is both even and odd. Well, that can't be, right? An integer can't be both even and odd. So that means your assumption, your original assumption, had to be false. So that means, therefore, the statement is true. So we're going to do that. So suppose the plot, or let's say, suppose the curve above corresponds to some function f, which goes from the set A to B. Okay, so this is a proof by contradiction. We're gonna say we want to prove that this vertical line test is true. And we want to, so that what we're proving basically is that if you have a curve and you have a vertical line which passes through it twice, then there does not exist a function corresponding to it. We're going to prove that by contradiction by saying, suppose there does exist a function that corresponds to it. And then we're going to show that this gives a contradiction. So what's important here to get this contradiction is that the vertical line here intersects at 2 different points. And for that to be the case, we have to have that B does not equal C, okay? B does not equal C. So now, if you look at this graph, then what this says is that f of A, well, okay, so if you plug in, what this says, if you read what this means, is that if you plug in A to the function, you'll get B, but you'll also get C, right? F of A will also equal C. But B and C don't equal each other, so that implies that f of A does not equal f of B. So plugging in A into f of x gives 2 different outputs. But this contradicts what it means for f to be a function. So this contradicts the definition of a function. Hence, there is no function which corresponds to the above curve. Now, don't worry about this if you don't follow this quite a bit. This is actually pretty abstract, and this is when you do things like this, there's a whole course based on this called proof methods. And if you plan on maybe studying mathematics any further, or is majoring in it or something like that, you'll take this proof course, and they'll discuss this method of proof, this proof by contradiction, in much more detail. But this is like one example of a proof by contradiction. You assume the very opposite of what you're trying to prove, derive a contradiction, and then that shows that what you assume to be false actually has to be true. Otherwise, you get a contradiction, and contradictions are bad, apparently. You can't have contradictions. Contradictions don't obtain in real life. So anyways, if you don't understand this fully, what's going on here, that's fine. I just wanted to illustrate to you and prove to you why the vertical line test is true. So let me just read this again. So a curve, this is the vertical line test, and I gave a partial proof of it. So the vertical line test states that a curve in the coordinate plane is a graph of some function if and only if no vertical line passes through the curve more than once. So we gave sort of a proof or an example of the case where you have a curve and there is a vertical line which passes through 2 points. And what we proved is that if this is the case, then there can be no function corresponding to this curve. Because if you suppose there is a function that corresponds to this curve, you'll have that when you plug in a number to the function, you get 2 different outputs, and that can't happen. That breaks the definition. That goes against the definition of what it means for f to be a function. So let's look at another example of this. Hold on. So let's look at example 9 in the book. So example 9 has 2 parts to it, and we're asked to determine whether the equation corresponds to a function where y is a function of x. So let me actually just write that down. This is the overarching question for both parts. So the question is, does the equation define y as a function of x? So for the first part, we have the following equation: y minus x squared is equal to 2. For this, the answer is yes. It's pretty simple because you can solve for y. When you solve for y, you get x squared plus 1. And no matter what value of x you plug in, you get exactly one value of y. And you can just test this with a few examples. You can plug in 1. When you plug in 1, you get y is equal to 3. That's exactly so. So there's only one value of y corresponding to the value of x equals 1, namely 3. And you can do this with a bunch of other examples. So this shows us that this is an algebraic way of showing that this defines a function. So you just explicitly solve for y. And if you plot this, you can see that if you plot this equation, you get a parabola shifted up to y is equal to 2, something like this. And if you just draw a bunch of vertical lines, you'll see any vertical line intersects at exactly 1 point. So it passes the vertical line test. When you draw the curve corresponding to the equation, it passes the vertical line test, and therefore there exists a function whose graph is this curve. So this is a plot of y is equal to x squared plus 2. And when you plot the equation, you see that it satisfies the vertical line test. Now let's look at part B. We're going to ask that same question, the question being, does the equation define y as a function of x? So the equation is the equation of a circle. So you can see the circle, it's a circle whose center is 0, 0, and the radius is equal to 2. Well, let's try solving for y. So if you subtract x squared from both sides, you get 4 minus x squared. And now we want to just get y. We want to isolate y in some way. So we'll take the square root. If you take the square root, you get plus or minus 4 minus x squared. Well, this is, as you can already immediately see that this is not going to work. So this is not going to be, when you plot this equation, the graph of this equation, the curve, this will not give you a function of y in terms of x. If you plug in 0, then you get y is equal to plus or minus 4 minus 0 squared. And then you get plus or minus 2 when you simplify this. So this has two outputs corresponding to one input. So this cannot be a function of, equation does not give us a function of y in terms of x. And this can be, so this is an algebraic way of seeing why this is not a function. But there's also the geometric way using the vertical line test. So we have a circle, not a perfect circle, but it's good enough, centered at 0. And the radius is 2. And if you draw, say, a line here, vertical line here, you see that it intersects at 2 points. So it does not pass. So the graph of the equation, or maybe I'll say the plot slash curve corresponding to the equation doesn't pass the vertical line test. And therefore doesn't correspond to the plot of some function. So we saw two different ways to show that this equation does not define y as a function of f or x. The first one was this algebraic method to just simply solve or attempt to solve y as in terms of x. And when you do that, when you take the square root, it gives you a plus or minus root. And that's precisely why this can't be a function. Y can't be a function of x, because when you plug in a value, any given value for y or for x, you get two values associated to any given value of x. So for example, if you plug in 0, there's two outputs corresponding to 0, namely plus or minus 2. So this is just an example. This one example or this one calculation shows that this y can't be a function of x. Y can't be a function of x. But you could also plot the equation, and the vertical line test will show you that y can't be a function of x. So this is, I think that's all for now. Actually, I'm just going to show you this picture right here, this table of some graphs, some functions and their graphs. So this first one is a line. You really actually have 3 cases. Actually, no, you don't. So I was going to say you have the vertical line also, but obviously a vertical line doesn't satisfy the vertical line test, right? Namely, you just look at the line, it's the vertical line itself. So that a vertical line will not correspond to the graph of a function. So for lines, we just have these 2 cases. These are linear functions, they call these. So linear functions are of the form mx plus b. This first one corresponds to a slope of 0, and this other one corresponds to a slope that is non-zero. Then you have these power functions, x to the n. So the first one is x, where when n is 2, so it's a parabola. Then you have x is 3, and I have this second plot here, x is 4, this almost like a parabola, but not quite. And then you have x to the fifth, so n is equal to 5. And then you have these root functions, and you have these reciprocal functions and absolute value function, the greatest integer function. So you can look at these to give you an idea of what some of these plots look like. And then we'll look at some more later on, and they'll just be sort of various transformations of these graphs. So that's all for 2.2, and I'll probably record 2.3 later on today.